max which the signal can take and x min which the signal can down to, the difference between these two extreme ranges is called dynamic range. And dynamic range is defined as x maximum minus x minimum. So here we have a 0.7 as x maximum and 0 as x minimum. So 0.7 minus 0.0 gives us 0.7. So 0.7 is the dynamic range defined for this signal. Now the next thing we are going to decide, now this has to be decided by the designer with the input from the user and some other considerations as well. This signal starts from 0.3, comes down to 0.1, then goes up and reaches value slightly over 0.6. Now it is up to us that between this x minimum and x maximum, how many levels we define. So if we are not concerned with the quality of the signal a lot, then we can say that okay, let's have just two inputs. Let's have 0 and let's have 0.7. Define as either the signal will be on this level or this level. Then as long as the signal is between is less than 0.35, whatever value you have, you will round it off to this level, and as soon as the signal goes above 0.35, you will say that okay, now the signal has gone up and is now closer to this level, so I assign this level. In that case there will be two levels, 0 and 0.7. But in this case we have decided to have 8 levels at a difference of 0.1. So first level is 0.0, the second level is 0.1, the third level is 0.2, 0.3, 0.4, 0.5, 0.6 and 0.7. And depending on the individual values of the discrete time continuous valued signal, we round them off and convert them into a discrete time discrete valued signal. So you can see that a value 0.283, near 0.283, there are two levels, one below which is 0.2 and one above which is 0.3. Of course this is closer to 0.3, so it moves to 0.3. So a discrete time discrete value signal will call a 0.283 sample as a 0.3 sample. And similarly the next sample is 0.155, which is although in the middle, but numerically it's very closer to, it's slightly closer to 0.2, so it goes to 0.2. 0.120 is converted to 0.1, 0.197 is converted to 0.2, and so on. So you can see that once this quantization happens, which is represented on the plot by the purple crosses, then we get the values as 0.3, 0.2, 0.1, 0.2, 0.4, 0.5 and 0.6. Now the difference between discrete time continuous valued signal and the discrete time discrete valued signal, you can see there are differences. Now this difference is called quantization noise. So you measure the difference between these two samples and measure the difference between these two samples and then measure the difference between these two samples and add them up, all samples differences, then we get quantization noise. So if you want to keep the quantization noise low, then we have to increase the number of levels. So if I increase the number of levels from 8 to 16, the error, the quantization noise will further decrease. And if I go from 16 to 32 levels, these levels will become even finer and will allow you to have even minimum quantization noise. But of course, when we increase the quantization levels, then it will also have some effect on other aspects. So let us look at those now. So coming back to the discussion, that in this example we have 8 levels. We have called them, if you look on the right hand side, we call them level 0, level 1, level 2, 3, 4, 5, 6 and 7. And on the left side we have represented those levels as L0, L1, L2, L3 and so on up to L7. Now to represent these levels in binary form, we see that these are 8 levels, and in order to represent these 8 levels in the binary format, we will be requiring 3 bits per sample or per level to represent all the levels completely. And this is because 8 levels are there. So if we take the log to the base 2 of 8, we end up as 3, which gives us that we will need 3 bits. So we define level 0 as 000, we define level 1 as 001, 010, 011, 100, 101, 110, and 111. So these are sort of addresses, binary addresses, which we define to these levels. And essentially, these are nothing to do with the values of these levels, 0.3, 0.4, 0.5. These are not really associated with them. These are the addresses for these levels. So once the quantization is done, which is to convert a discrete time continuous valued signal into a discrete time discrete valued signal, then we have to convert these into a bit stream, which is called a coding process. So what we do is that we have the first sample as 0.3. So we look at that, okay, this is level 3, so we call it level 3. 0.2 is called as level 2. 0.1 is called level 1. 0.2 is called level 2, and so on. So now we have the signal values coded as levels, and then we can assign the bits to these levels. So L3 was 011, so instead of L3 now we have 011. L2 was 010, so we have assigned 010, and so on. So now you can see that we started with an analog signal which is going like this. It went through a sampling process. Then we converted the sampled signals into the rounded off versions, which are quantized signal, discrete time, discrete valued signals. And then these signal values are converted into levels, and then levels are coded into bit streams. Now this is the entire analog to digital conversion process represented on this slide. These levels are called quantization levels. The difference between, or the distance between, two consecutive quantization levels is called quantization step. In this example, the quantization step is 0.1, difference between 0.5 and 0.4, or 0.3 and 0.2, or 0.1 or 0, whatever. You measure the difference between two consecutive quantization levels. This gives us quantization step or resolution. So I hope with this slide, we took a bit longer on this slide, but the purpose was that all quantization processes and their definitions are merged on one slide, so that whatever comes next in this lecture, it is easier for you to grasp.